Okay, so hello everyone. So I'm Niall McLaughlin and I work at CSIT, Queen's University Belfast. So just here's a picture of a building where I don't work anymore, and there's my office where I don't sit anymore. So I'm just at home like everyone else for many, many years. So CSIT is a big research center at Queen's. So we have lots of researchers doing work on everything from quantum encryption, post-quantum encryption, hardware security, software security, network security, and malware detection, which is what I work on. So I've tried to keep this talk at a fairly accessible level. So what I'm going to try and cover is basically just some work that we've done over the last few years in the area of malware detection and malware analysis. So I'm trying to keep it at a fairly, easy to follow level. So if people are not experts, not working in this area, hopefully everyone will still be able to get something from the talk. And as well as that, so if you want to jump in and ask some questions at any point, feel free to do that. So I'll cover these topics. I'll cover basically some work we've done quite a few years ago now on opcode sequence-based malware detection. I'll talk about how that was extended to basically be robust to some obfuscation techniques, and then talk about some very preliminary recent work on explainability. Okay. Right, so why do we want to use deep learning for malware detection in general? Okay, so deep learning has obviously revolutionized the kind of world of machine learning over the last sort of 10 years or so. And the big reason why we want to use it is basically because we want to remove the need for manual analysis that people would have done in the past. So in the past, in obviously many different areas of machine learning, people would have spent years designing different features for whatever type of data that they were looking at. So if they were looking at images, maybe they spend different, years and years spending a lot of time coming up with different features to like recognize, cats based on, the type of fur it has, the shape of its eyes, the shape of its ears, all that kind of stuff. And obviously people do something like that as well for malware analysis. They would try to look at a program, figure out what are the important features, what are the kind of things that we should design programs to look for. So by using deep learning, we want to try and do away with all of that. We want to have one system where you just give it a file, it analyzes that file by itself, and it gives you the result at the end. So it's removing all of those kind of manual static analysis, manual feature engineering that people would have done by hand. So obviously the hope is that by doing that, you may be able to discover certain things that would not be discovered by human analysts. So this may be a double-edged sword, and I'll come back to discuss this a little bit later on when we talk about the explainability, because obviously when it discovers certain patterns, it may be discovering spurious correlations in the data rather than actually something which is important. So we'll come back and discuss that later when we talk about explainability. The other thing which I think maybe is a bit underrated with deep learning in general is the fact that this is actually quite a simple kind of way to write programs. Okay, so in the past, if you wanted to analyze a piece of malware, you would have had to spend a really long time developing all of these manual feature extraction methods, different machine learning classifiers, different feature selections. Lots and lots of software would have to be written. In theory, at least, with deep learning, you could just give it a file, it does some analysis in the neural nets, learns everything itself, and it produces the results. So all you actually have to provide is a data set, some labels, a deep learning system, and it actually does everything automatically by itself. Okay, so it may not actually work out like that in practice, but that's the hope, that eventually systems would be able to work like that. The other thing is that we would hope that these systems will be more scalable and more robust. So obviously manual analysis of malware by hand is a very time-consuming process. We'd like to be able to just run these things very efficiently, very quickly, and do away with all the kind of manual analysis. And so when I mentioned here about discovering patterns that might not be discovered by a human, that kind of leads into the robustness part of this as well. So we want the system to be robust against all the kind of variations and changes that happen as malware evolves over time. So every single day, there's new malware coming out, being created by people, being variations of existing malware. So obviously it's impossible for anyone to keep up with all of that change that's happening, in the real world of malware. Something called concept drift, which just means that your distribution of malware is changing over time, and you have to somehow keep up with that. So the hope is, by using machine learning, by using deep learning specifically, we'd be able to keep up with the really fast-paced changes that are happening in the malware environments. So the final thing is just that once you've built your system, once you've got this neural network for doing malware detection, it can be very, very efficiently executed by GPUs. Okay, so what that means is that you can run this on mobile applications. So almost every mobile phone now has a very, very powerful GPU, which can run deep neural networks very, very fast. And you can also do potentially very high volume checking of files over network. So obviously, if you have a big network, you may have maybe thousands and thousands of files coming in all the time. You need to be able to scan those files very quickly and check if there's malware presence. So by building a neural network-based malware detection system, running on the GPU, it's a very efficient, very fast way to do your malware detection. So those are the kind of general ideas. Why would we want to do deep learning for malware detection? We'll look at now some specific techniques that we've developed to do that. Okay, so this was done quite a few years ago now. This was a paper that we published back in 2017, it says here. So what this was we wanted to take some existing techniques that were developed for NLP, natural language processing, and apply those to static analysis of Android malware. So malware analysis, there's two different ways to do that. One is static analysis and one is dynamic analysis. Static analysis basically means that you take a file, you don't try to run it, you just try to analyze the file as it is and get out a decision, is it malware or not? Dynamic analysis involves actually running the file. Okay, so there's two different ways. You look at it without running it, do some analysis, get a decision, or you actually run it, observe what it does, observe its behavior, and then get a decision that way. So our method is primarily for static analysis. We just take a file, do some computations on it, says malware or not, but it could also be applied to dynamic analysis. And so what we're trying to do is we're trying to take, just go on to the next slide. Basically, we take an Android file. So an Android file is something called APK. So an APK is basically a Java file. So Android apps tend to be written in Java. So you take that file, you decompile it. So we get some open source tool for doing that. APK tool allows us to decompile existing Android apps back to their original class files. Okay, so in those class files, we can get back something called the Dalvik bytecode. So in Android, basically stuff is written in Java, it runs on a virtual machine on the phone. We get back the bytes or the bytecodes for that virtual machine. Okay, these are the instructions that run on the virtual machine. So what I'm trying to show here is that we've taken an Android APK file, we've decompiled it, and we've got back the bytecodes. So this is actually the instructions inside one method inside some Java method inside of this program. So we take this Java method, and it seems quite complicated here. Okay, there's lots and lots of different things going on. Really what we want to do is we want to understand what's its behavior. Okay, so we want to figure out what is the app trying to do, and that will tell us if it's malware or not. So what we do is we take this decompiled bytecode, and I hope you can see my cursor here. We strip away almost everything. What we're left with is a sequence of the opcodes. Okay, so we discard the operands, which are all these other things over here, like basically the arguments for each instruction, and we're just left with the opcodes. Okay, so these opcodes tell you what is the function trying to do. Okay, it's a list of all the operations performed by this function. So if we do that for the entire APK file, for the entire app, basically, we get back a big list. Okay, so it may be millions of opcodes long. That tells us something about the behavior of that program. Okay, so we're able to try and analyze that and figure out what is the behavior of this program. Is it trying to do something malicious or not? So just to summarize, we take our APK file, decompile it, get back the original source code, throw away everything except the list of the opcodes. So we have this list of opcodes, convert them to some kind of numerical representation, and then pass them into our neural network. Okay, so it can predict if it's malware or clean. So what this is really trying to do is to treat the sequence of instructions as a kind of text. We want to take this piece of text and figure out, is there some pattern in that text that can indicate if it's malicious or not? So we'll look at the overall architecture of our network next. Okay, so this is the overall diagram of how our network works. So it starts off here at this side with the opcode sequence. And like I said, this is what we get by pre-processing that Android APK file and getting back the list of all the different instructions inside of the file. So like I said, this can be applied to static analysis, where we take the file, get back, decompile it, get the list of instructions, and then analyze it. But there's also no reason why this can't be applied to dynamic analysis. If you have some program running on the processor, you can monitor the instructions being executed and do the exact same type of analysis. All it requires is a list of the instructions to do the analysis, and obviously retraining the network. So we'll talk about each of these different layers in turn, but basically what we're doing is we're taking the sequence of instructions and trying to find patterns in it. Okay, that's the overall goal of this network. Try and find some patterns that exist in sequence of instructions. Some of those patterns will indicate malware, some of them will indicate clean software, and we're training our neural network to do that with a big data set that we collected. So let's go in and look at the different layers of this neural network. So the first thing we have is something called an embedding layer. And I find sometimes people are a bit confused about why this is necessary, but basically these instructions, okay, we take the sequence of instructions from the Dalvik bytecode. These are just, instructions that run on the virtual machine, and they get assigned arbitrary numbers. Okay, so maybe moving, a byte from one register to another has one number, or for example, adding two numbers has a different number, a different representation. But ultimately, these are just arbitrary. Okay, so why should the instruction for, copying something from one register to another be represented by, 58? And why should the instruction for, adding two numbers together be represented by 17? Okay, they're just arbitrary numbers. They don't mean anything. So what we want to try and do is to give the neural network a way of learning its own representation for each of the different instructions. And this is kind of like the word2vec you may have seen in natural language processing, where it takes a word and finds some kind of vector that represents the meaning of that word. So in our case, what we're trying to do is we're taking an instruction and we want to find some kind of vector that represents that instruction. And the vectors encode the meaning of the instruction. So what we're saying is that they start off, when we start learning, they're just all random. Okay, and as we train our network, gradually what we find is that instructions with similar semantics, with similar meanings, will somehow move closer in this representation space, this embedding space. So at the end, what we would expect is that instructions which have similar meanings, similar semantics, will be somehow close in the embedding space, and instructions which have very different meanings will be very far away in the embedding space. And so what you end up with is a list of vectors, and each vector somehow tells you about the meaning of that instruction. So the neural network has learned the meaning of the instructions by being trained. So what does that look like in practice? Okay, so what I've done here is I have taken the embedding vectors. Okay, so these start off as like long vectors. So we have instruction over here. So for example, 0, 1 gets converted into a vector. And what I've done then is I've taken these vectors and I have done a projection of those into 2D space using tsne or tsne, however you want to say it. So what we find is that if we look very closely here, you'll find that instructions which are similar to each other are going to be close in this space, and ones which are different from each other will be far away in the space. So if you look up at there, you can see things like there's some if statements are close to each other, some kind of conversions from different types are all close to each other, and various other things. Okay, if you looked at that for a while, you would be able to see some interesting things going on. Okay, so what's happened here is the network has learned its own representation for each of the instructions in the instruction sets. Okay, so that's our first part of our network. So once we've done that, we've taken our sequence of instructions and we have projected them into this embedding layer. Okay, so each one now is represented by a vector. We want to try and find patterns in this sequence. Okay, so the opcode sequence here is all of the instructions in the whole program, just concatenated together. We want to somehow find, are there patterns in this that can tell us if it's malware or not? So to do that, we're going to use something called a convolutional layer. So obviously these are used for images very extensively. So convolutional layers are slide over an image and tell us, are there certain patterns present or not? We're going to use the same principle to find patterns in the malware sequence of opcodes. So what we do is that we take our embedding layer here. Okay, so this has taken the opcode sequence, projected it to a sequence of vectors. and we want to slide a filter over this matrix to find, is there a pattern present or not? So literally what happens, I'll just show you with this diagram. We start off at the first place, okay? So we apply our filter and we get a score, and it tells us how well does this filter match at this place. Slide the filter along again, check how well does it match at this place. Okay, so we keep doing that for the whole thing. And basically it tells us at each location, how well has the filter matched at this location? Did it find the pattern it was looking for or not? So obviously one filter isn't enough. We have to have lots of filters to be able to detect lots of different patterns, because obviously there are lots of different malware types out there. So we run lots of different filters over the sequence, and we get back a list of numbers for each one of those, okay? And each of these lists of numbers is the same length as our opcode sequence. And what it's saying is, did they match well at this location or did they not? So we can see here 0.7, maybe at this location it found a really good match, whereas maybe at this location it didn't find a good match. Okay, so we're sliding along trying to find some patterns. And all of this is learned by the network. We don't have to tell it to look for a certain pattern. It learns how to do that for itself. So in our final network, we use 64 filters. Probably that's because our data set wasn't that big. If you had a bigger data set, you can just use more filters and you get a more kind of ability to match more patterns, basically. Okay, so once we've done that, we have slid all of our filters across our embedding matrix. We have got a series of numbers, and we're trying to figure out, how can we summarize this thing into some smaller vector? Because look at what we've got, okay? So we started off with this opcode sequence, and maybe this was, for example, 1 million opcodes long, okay? We projected it using our different convolutional filters, and it may, for example, we have 64 of these, and this is 1 million. This becomes a really, really big matrix, okay? So it's 1 million in this dimension, 64 in this dimension, so 64 million numbers. It's a huge matrix. We have to somehow try and summarize this to get a small representation of that piece of malware. So we wouldn't be able to pass this whole thing into, for example, a classifier because it's just too big. So to summarize this, we do something called max pooling. It's very simple. All we do is we take the maximum along each of the columns. Okay, so by taking the maximum along each of the columns, this huge matrix, which might be starting off as 1 million in height and 64 in width, suddenly reduces down to a small vector of, for example, 64. Okay, I've shown 4 here, but in reality, this might be 64 elements long. So this vector is the representation for our piece of malware. Okay, so it tells us something about this piece of malware. What it's basically saying is how well did each of these filters match. So for example, this filter didn't match very well, and these two filters matched much better. This one matched very well indeed. So this keeps the relevant information. Basically, it's a sparse representation of this piece of malware. So we've started off with a big sequence, and we've ended up with just a little vector at the end that somehow represents that whole piece of malware. So given this little vector, we can then pass that into a classifier. Okay, so nothing complicated here. Just pass it through a multi-layer perceptron with, for example, 16 neurons, and then into a softmax classifier. So one thing to note here is that this network is actually very, very small. So after setting this all up, roughly has around 10,000 parameters, which is actually very, very small. For any kind of neural network, these days you might have millions or even billions of parameters. This one has 10,000 parameters. Okay, so really, really small. Helps us to stop overfitting. And the reason why we want to do that so much is basically because the malware data sets that we're working on are very, very small themselves. Typical malware data sets, you may have a few thousand examples, maybe tens of thousands of examples. So you really don't want to be using a giant network with millions of parameters because you will just overfit. So I'm not going to go into the full details of how we evaluated this. You can obviously look up the paper. I just want to mention a few things. So we were comparing this. So at the time when this was done back in 2016, some of our colleagues had developed a classifier based on n-grams. So that's just taking short subsequences of opcodes and trying to build an SVM classifier based on those short n-grams. So they had developed this system. We were comparing our CNN with theirs. And what we're saying here is how many programs per second can you process given a certain number of n-grams, or a certain length of n-grams, sorry. So if they were using 3 grams, so that's sequences of opcodes of length 3, they could barely process 1 or 2 programs per second. The CNN, by the way, was processing 3,000 roughly programs per second. And how does that compare with the n-gram system? So this system, as you increase the length of the n-gram, its performance improves. Our CNN, the length of the n-gram is basically the length of this convolutional filter. So by making this convolutional filter longer, you increase the effective n-gram length of the CNN. So in our case, we were effectively using n-gram of length 8, which would have been actually impossible with this conventional machine learning classifier based on SVMs. So what we're showing here is that our system was basically much, much more efficient than classifiers back at that time. We also wanted to check that we were not overfitting to our data sets. So to do that, we used this thing called learning curve. And what we basically did was we held our validation set the same, but we varied the size of our training sets. Okay, so what we're saying is that let's plot for a given size of training sets, what is our validation error and what is our training set error. So if your training set is very, very small, okay, down here, obviously you'll get a very, very low training set error, but your validation set error will be very high. As you increase the number of training examples, what you tend to find is the two things will converge towards each other. Okay, so we increase our number of training examples. Obviously, our training set error will increase, but our validation set error will decrease. And what we're showing here is basically that we're up in this regime here at the top, where the validation set error, the training set error are decreasing and coming closer to each other asymptotically. And what it basically means is that our classifier is benefiting more and more from increasing training data. So go back. So basically what we're showing is that we're not overfitting, and by adding more training data, our classifier would continue to improve, if we just were able to give it more training data, which we didn't have at that time. So the final thing here, so obviously on our little data set that we developed this on, we had very high accuracy, 99% or whatever, but really that's not that important. It's not that kind of relevant to the real world. We wanted to try and do an experiment where it was more realistic. So we worked with some colleagues at Arizona State University, so ASU, and basically they collected a very large number of APK files back in 2016. And they did this experiment for us. So we gave them our classifier, we had no control over this, and they ran the experiments for us. So we had trained this on our own internal data sets, which was given to us by McAfee, so antivirus company. Roughly 16,000 APKs in that data set, so 8,000 malware, 8,000 clean approximately. They collected this other data sets, which was much bigger than our one. So they had almost 100,000 clean or benign and roughly 24,000 malware programs. And these were different from the ones that were in our training sets. So no overlap between the testing that they did, no overlap with that and our training sets. So they basically evaluated how well did our classifier work, and they got an F1 score of roughly 70%. You may say that that's not very good, but actually I found that this is actually quite impressive in a way, because there's no overlap between the training set, the testing sets. Testing is done on a much larger data set, and we had no way to fudge these results. Again, they were done by someone else. And also the fact that we're only using opcode sequences, we're not using any other additional types of features, which is what you would do in real life. So it actually shows that the classifier has potential to work, and we do know that it works much better these days when we have much more data to give to it. So just a quick summary of what we did there, and we'll move on to the next things in a minute. So this is back in that time, 2017. We developed a static analysis system for Android malware. Basically showed that this is a general type of system. So if you were able to give it a different training set, you could apply it to different platforms. And it reduces the need for manual static analysis. It's competitive with the existing approaches back at the time, so it was better than the existing n-gram-based approaches, and it was very, very much more computationally efficient. And we also showed that it would benefit from more data if we were able to provide it. So I next want to talk a little bit about how we extended this system to be more robust to obfuscation. So this is work, okay, so I'll talk about this first. So basically the real malware uses many different techniques to try and stop people from detecting it and being able to analyze it. So lots of different techniques, for example, packing, which is basically zipping up the code into a little package, then you unzip it into memory when you want to run. You have obfuscation, which we'll come back to in a minute. And we have metamorphosis, which is just changing the code in different ways. So obfuscation is the thing we were going to tackle. And what happens in obfuscation is that you run a program on the malware code, it changes it, but it tries to preserve the meaning of the code. So some very, very simple ways to do that. Imagine you have a list of the instructions in your program, assembly instructions, and you just insert a whole bunch of no operation codes into the assembly. Okay, so the meaning of the code would be the same, but it might look different to a malware classifier if you put in a whole bunch of no operations in everywhere. So that's a very, very simple way of obfuscation. Obviously, there are more complicated ways to do that, where it's really messes up the code, but it preserves the meaning of it. And the overall point of this is to try to stop malware classifier from working as effectively. So we asked the question, can we extend the architecture that we developed to be more robust against obfuscation techniques? So this is work done by Stuart Miller, who was one of our PhD students who recently finished the PhD. And we'll talk about this now. Okay, so the first thing that we did was we needed a data set to work on. So we used the DANdroid data sets. So this consists of roughly 5,000 malware apps from different malware families. We also had a bunch of clean apps collected from the Google Play Store. So what we did was we took this DANdroid data set and we applied a lot of different obfuscation methods to it. So we used this tool, Dex Protector, which is able to automatically apply obfuscation to Android APKs. So what we ended up with at the end was 5 different copies of the data sets, each of which has the same apps, but with different obfuscation methods applied to it. Okay, so what are the different obfuscation methods? So we have class encryption. So this classes.dex is basically the where all those opcode sequences are stored in the APK files. So we encrypt that in some way. We have different ways of obfuscating API calls. So obviously programs need to call the operating system to do things. So there's ways to hide that this applies. We can encrypt the strings. Okay, so every app has a bunch of strings in it. For example, error messages, menus, anything you want to say to the user, those are the strings. So obviously that strings are quite an important feature for malware detection. So this thing, Dex Protector, can encrypt the strings. We can encrypt the resources. So resources are just like, anything the app needs, like icons or, menus, whatever. Those can be encrypted. And we can also do the combination of all of these things together. Okay, so we end up with 5 different copies of the data set with all these different obfuscation methods applied to it. Okay, so this is our modified architecture. You may see it's slightly different from what I showed last time. So this one in the center, this is basically the standard CNN that I showed last time. Okay, so we're taking an opcode sequence, passing it through the CNN. Everything is the same as we did last time. But we also extend this to incorporate multiple different types of features. So for example, we can extract the API calls, we can extract any kind of Linux commands, any kind of terminal commands. All that stuff can be extracted and passed in as a vector to the classifier as well. And we also can extract the permissions. So whenever you run an Android app, it will ask you, can I please use your camera? Can I access your address book? All this kind of stuff, our permissions can very easily be extracted from the APK file. So we have API calls, we have the opcode sequence, and we have the permissions that the app requests. So these are the 3 different, well, there's actually more, but it doesn't matter. These are the 3 different types of features that the classifier is going to use. So same as before, we extract all these different features, pass them through different neural nets, 3 different branches of this neural net. And at the end, we get out 3 different feature vectors, which summarize the different features that went in, concatenate them together, pass them into a classifier, and obviously it says, is it malicious or benign? Okay, that's the basic malware classifier, as you would expect. So we somehow have to extend this to be robust to obfuscation. Okay, so let's look at how we do that. So to make it robust to obfuscation, we add this second branch to the system. Okay, so this branch, what it's doing is it's predicting a label. And instead of predicting malware or clean, what it's predicting is this sample obfuscated or not? Okay, so we have our data sets. We have applied obfuscations. So we know for each sample, has it been obfuscated or not? The second branch of the classifier is able to predict that. So it looks at the malware sample and says, has this been obfuscated or not? So obviously that's not going to help you on its own, or will help you a bit, but it won't help you the full way. So we need to do something else. Okay, so then we apply this thing called a Domain Adversarial Network, or DAN, which is why we call this the DANdroid architecture. So the way that this works is a classifier runs just standards. Then we have two different branches. Okay, so this one is predicting malware clean. This one is predicting obfuscated or not obfuscated. And the difference comes whenever we apply backpropagation. So what we're trying to do here is that we reverse the gradients from this branch of the network during backpropagation. So rather than doing standard gradient descents, we actually just flip the sign of all the gradients from this branch. And what this effectively is saying is that this representation that we have here in the middle, this should be invariant to whether the app is obfuscated or not. Okay, so what we're saying is try to learn a representation that is the same whether the app is obfuscated or not. So it's invariant to obfuscation. And we do that by reversing the gradient during backpropagation from this branch. Okay, so some of the results that we got from that. So what we have is two different ways of training it. Standard training, which means that we don't apply any of the obfuscation during training. So we just train it with unobfuscated samples, but we test on obfuscated ones. Okay, so during training, there's no obfuscation. During testing, we do apply obfuscation. We can see that when we apply the obfuscation, obviously the results for malware detection get much worse. Then we do training and testing, both using obfuscated samples. We do this with and without the domain adversarial network. Okay, so that's with and without this branch over here. So what we can see is that we do get an improvement by doing our training with the obfuscated samples, and we get a further improvement. Okay, it might not be that much, but we do get a further improvement by applying this domain adversarial network. Again, it's an active area of research, and we can seek to kind of further improve this in future. But what's basically happening is it's kind of saturating at this level. So probably what we need is a larger data set to be able to reveal if there's a bigger change in these numbers. So what we're saying is by applying domain adversarial training, we're able to improve the robustness to obfuscated samples. So just a summary of what we've done there. We've taken our existing CNN architecture for detecting malware based on opcode sequences. We've extended it to include this domain adversarial loss. We've changed the type of features that it takes in to make it more robust. And we've shown that we can improve its robustness to obfuscation. So the same methods of applying domain adversarial training could be used to deal with other types of attacks. So I said here adversarial attacks, which is a big area of research these days, and that's something that we're looking into at the moment. Can we take this method and extend it to make the classifier robust to adversarial attacks? Okay, so we'll cover this final topic, which is really just a very preliminary thing that I've started to work on with a PhD student in the last 6 months or so. So there's not many results on this, but I think it's something which is it was interesting and always sparks quite a bit of debates when I talk to people about it. So we have these big neural networks. Okay, we can do very successfully recognition of images and image nets. We have giant networks like GPT-3 that seem to be able to have conversations with people. Deep learning seems to be very, very successful. Okay, we can build these giant networks and they get great accuracy. They can do seemingly amazing things. But there's some cost to doing this. Okay, so we have very complex neural nets. They're really, really big. There's massive amount of computation. We don't really understand how we're getting from the inputs to the outputs. Okay, so something is going on. We don't really have any understanding of what's going on inside of our neural network. The other thing is that we don't understand, what are the factors, what are the features that are being used to make decisions. We just take a lot of data, plug it into our network, produces the answer, but we don't really understand what are the features being extracted from that data to make a certain decision. And the final thing is that it becomes very, very difficult to debug these models. If anyone has done any work on transformers, you'll realize that figuring out, I have this giant model with, billions of parameters, trying to debug it, trying to figure out how can I change the hyperparameters is almost impossible. So we need to somehow care about explainability. And there's a few reasons for that. So the models that we're creating, even though they seem to be very successful, can actually be very, very fragile. So an example of that would be adversarial examples or the different catastrophic mistakes that we see in, for example, self-driving cars. So adversarial examples are basically a way where you add a small change to the inputs and suddenly it causes a huge change in the output. So I might take an image of, a cat, I change 1 pixel, and the neural network thinks it's a dog instead. Whereas a human would look at that and they would not, have any problem recognizing it if 1 pixel has been changed. We also have a problem of examples outside of the training distribution, and this comes up a lot in malware. Because obviously in malware, people are constantly trying to create new malware, trying to get around defenses, and the distribution that you're testing on is going to be different from the training distribution, and that constantly happens, as malware changes over time. So really, all of these things add up. We have this really big problem now where we're deploying these neural networks in the real world. We don't have any insight into how they really work, and we probably put too much trust into the neural networks. So I had someone say to me, a few weeks ago, a colleague basically was saying, I don't know how my doctor or my pilot makes decisions, but I trust them because they're able to pass all the tests. And I think that reasoning like this actually doesn't quite work for neural nets, because we're kind of imbuing them with human common sense and understanding that they don't actually have. So neural nets appear to work really well. Even on our training sets, they appear to work really well. As soon as we take them into the real world, they will come across examples that they've never come across before, and they'll actually not be able to make sensible decisions on those examples. A human has common sense. They have all this additional knowledge. They're able to fall back and do certain reasoning. Neural nets are really just a kind of reflexive system. They look at an input and instantly make a reflexive judgment on that. That's really not how people make decisions. So there's a big difference between neural nets and human reasoning. And in order to really kind of uncover what are those differences and figure out, are there real problems with how the network is working? Is it using the wrong type of features? Is it doing things the wrong way? We have to sort of think a bit more about explainability and develop systems that can have explainability built in. So to do this, we were using a thing called LIME. So I'm not going to go into the full details of how LIME works. You can look up the paper. But basically what it's able to do is identify the important features of the input. So you give an input and it's able to say, what are the features of this input that are correlated with a certain label? So in this case, what I've shown is this very strange example that's always used with LIME. We're saying, what are the features correlated with electric guitar? So it's, this part of the guitar. What are the features correlated with an acoustic guitar? So with these kind of wooden parts. And what are the features correlated with this type of dog, Labrador? So it's the face of the dog. So can we do something like this for malware? So given a piece of malware, can we identify the parts of the file which contain the malicious payload, which contain the most important parts of code that we want to look at? So in real world, malware is just very messy. Okay, so real malware files, they don't have a label. They don't tell you this is a specific part of the file where the malicious code occurs. You just have a whole file. If you're very lucky, that file will have a label. It will say this is malware, but it doesn't tell you at line number 47 of the source code, that is where the malicious function starts. So we need some way to be able to investigate this, and doing it with realistic data sets, probably too challenging at the moment. So a possible way to approach this is to create synthetic malware. So if we can create a synthetic piece of malware where we know locations and malicious functions, then we can run our explainability method on that and check if we can recover locations of the malicious code. So given a file, we create an artificial piece of malware, we know where the malicious code is, we run it through the explainability method, and we say, can we get back locations of malicious functions in that file? So some very, very preliminary results on this, which has just been done recently. So this is an example of a file. So here I have an opcode sequence, and this is the length of the opcode sequence, just very short, roughly 2,000 opcodes long. There are some artificial malicious functions put in here. So our ground truth is basically saying that these parts of the file are just uninteresting. These parts of the file contain some kind of malicious function. We run our explainability method on that and check, can it recover those locations? We can see that it can recover locations. There's some noise, obviously the classifier isn't perfect, and there's some issues with the explainability method, but in this case, it is able to recover locations of malicious functions. And like I said, this is just work that's really just started with the PhD students. Hopefully over the next few years, we'll be able to come up with something more concrete in this area. So this doesn't exist. This is just my kind of vision of what we would get in the future. So in the future, we take a file, pass it into IDA, do some analysis with our explainability methods, and we're able to get back, in theory, some kind of highlights where it says, these are the parts which are associated with malicious code. these parts are clean, they're not interesting. So what we're trying to do here is develop a tool for malware analysts, which helps them to focus on the really interesting parts of the malware file. And like I said, this is just my vision. This isn't something which is real, but hopefully in a few years, this is the kind of tool that we'll be able to deploy into the real world. So that's all for my talk. If anyone wants to contact me, that's my email address. I'm happy to take any questions that you might have.
Yeah, thank you very much, Niall, for your very interesting talk. So now we stop the recording and take questions. You can either raise your hand and we unmute you, or you can put your question to the comment section and we read them out.